Okay, let's look at section 9.2. 9.2 deals with linear regression and the coefficient of determination. So a linear regression is when you construct a best fit equation for your data set. And let me say, we're going to use a specific technique to find this best fit line. There are simpler ways to do this than the way we're doing it. You could do a scatter plot of your data, and then just kind of eyeball a line through that, and then just try to find 2 points on that line you eyeballed, and find the equation of that line using those 2 points, like you would in an algebra class. That is a simpler way, and if only want a rough estimate, then that's okay. We're going to look at a mathematical way to come up with what we're going to consider the best fit line using that technique. So ours is going to be a little bit more analytical about it, but in the real world, you might just, if you just want a quick estimate, you could do, just scatter plot and just kind of do it like that. I remember when I was an undergraduate and I took science classes, and we would do experiments, and we would want to do a best fit line. That's how you do it. But this way will be a bit more accurate in that calculation than just kind of, different people are going to draw that best fit line different ways if you just do it by hand. So this will be a way we all could get the same, roughly the same equation, plus or minus a little bit due to rounding, but that it would be much more accurate for that best fit line. Okay, before we calculate the best fit line, we're going to find some values. We're going to find the mean of x, right? So let me just go ahead and I'll label this. This is the mean of your x values. Again, the mean of your y values. We're going to find the sum of the x's, and you'll probably find that to find the mean. Right? Sum of the x's, sum of the y's, you're going to find the sum of the squares of x. And remember when we did that in 9.1, squares of x. You're going to find the sum of the squares of y. Right, you're going to square all the y values and add up all those answers. And we're going to find the sum of the products. Right, so we're going to multiply each xy pair and then add up all those products together. Right, so that's what we're going to do. Now, in algebra class, when we wrote the equation of a line, we wrote it as y equals mx plus b, where your slope or your rate of change, or a change in y or a change in x, or rise or run, you use all those different types of phrases in algebra classes. M, so was m, and then your y-intercept, where it hit the y-axis at, was at 0b. So this was called the slope-intercept form, this y equals mx plus b format. In our statistics course, though, we're going to use what's called the least squares line. And so it still has the same stuff, but it's going to be kind of in a different order here. So it's going to be written as y hat. So y hat's going to be our estimator for our response variable. And then your a, that's going to be the y-intercept value. So notice it's in the wrong, I shouldn't say wrong order, it's in a different order. It's in a different order. And in this case, your slope, we're going to denote with b and then times x, right? So another name for the slope is the marginal change. Now, again, a big thing, keep in mind, this b isn't the same b as y equals mx plus b. That is now a. So what was b is now a, and what was m is now b. All right, so just be aware of that the b here in our least squares corresponds to the m in algebra class with the slope. All right, so don't confuse those two. All right. All right, first we're going to calculate the slope, and this is the formula we're going to use to calculate the slope. So that's why we had to calculate all those sums. I said at the beginning, you're going to take your sample size times the sum of your products minus the sum of the x's times the sum of the y's. You're going to divide that by the sample size times the sum of the squares of x minus the sum of x squared. All right. So you're going to figure that out, and you can kind of notice on the bottom there, you're subtracting the x value. You're subtracting x values, and change in y over the change in x. That's like, oh, there's y's on top, but there's also x's and things. But this is how it's calculated. This is how it's calculated. All right. Once you know that, you're going to find the y-intercept. So we're going to use this formula to find the y-intercept. Y equals the average of y minus b times the average of x. Now, our equation is going to be y hat equals a plus b. So if you were to take that equation, and I would say, let's solve that for a, what you would do is you would move that over there, and you'd get a equals y hat minus b times x. So that's this formula. We're just substituting in the average for x and the average for y to do that calculation of what a has to be. And you might remember one way to find the equation of a line would be, once you know what the slope is and you know a point that the line goes through, you substitute that xy value in there to find the y-intercept value. And that's all we're doing here. That's all we're doing here. It's just, it looks different because our letters are different, but that's all that's going on here. All right. So let's look at page 563, number 12. All right, so number 12 here. Number 12, so let X be the age of licensed drivers in years. Let Y be the percentage of all fatal accidents for a given age due to the failure to yield the right of way. Okay, so they failed to yield the right of way. For example, the first data pair states that 5% of all fatal accidents of 37-year-olds are due to the failure to yield the right of way. All right, so that means like the other 95% are for some other reason. Failure to yield would be like, maybe you don't stop at a stop sign, maybe someone's trying to, or maybe you're supposed to merge and you don't let the other car go, you just kind of move over and you cause an accident, things like that. All right. So we have this data set. So make sure when you're doing the homework, you realize like the directions for 7 through 18 is on the bottom of page 561. And it asks you to do, well, starts there and goes on the next page. You have part A, part B, part C, part D, part E. Okay, and they let you know that your answers may be a little bit different based on some rounding that you might do. It should be in the ballpark. Shouldn't be too different, but should go from there. So for this, they gave us this data set, and they say for part A, do a scatter diagram for this. Now, looking at these, all these are obviously positive values. So maybe I don't need, when I'm looking at this, maybe I don't need this here. I'm gonna scratch these out, and I'm just gonna make the whole thing quadrant 1, right? So this is gonna be my x-axis, and this corner will be my y-axis. Okay, y-axis. Okay, so looking at these, I think the way we can count this is I can start, we'll do those just to indicate that this bottom corner is not to scale. And we'll just count by 5. So every line is a 5. So this will be 47, 57, 67, 77, 87. Okay, so that'll work out nice. On the other side, we have percentages, 5 all the way up to 43. I think we can just count by 5s. That'll probably work. 5, 10, 15, 20, 25. And obviously you're going to use, if you're drawing this by hand, whatever graph paper or whatever you need, 45, so on. All right. Here we go. So I'm going to start by plotting this. So at age 37, 5% can be explained without yielding. 47, 8% can, 57, 10, 67, 16, that might be around there. 77, we go up to 30. And 87, we go up to 43. So somewhere around there. Okay. So do the scatter. So we did that. And then verify the sums that are given and the value for the sample correlation coefficient. So I went ahead and did the table here, squared the X values, I squared the Y values, I calculated the products, I added all those up. And we're gonna wait on the R value till later, but I think these all correspond to the values. Yep, 372 for the sum of the X's, sum of the Y's, 112, that's the same, 24,814, 3194, sum of the products, 8254, so on. And we'll come back to the R value a little bit later. And I went ahead and calculated the average for the X's. So again, the way you calculate average, you add up all the X's. So 372 divide by how many are, and there are 1, 2, 3, 4, 5, 6. And I'm just gonna write that, n equals 6, okay? So we have that. And we're gonna go ahead and look at part C. So part C says find the average X, average Y. So I had those on the previous page, 62 and about 18.67. So average X, 62, average Y, 18.67. I think it's 18 and 2/3, but 0.67, close enough. And then find A and B, and then find A and B, then find the equation of the least squares approximation. Okay, so again, to find B, so we're going to use that formula, that big formula there. So let's get that out. So we're going to take our sample size, which was 6, times the sum of our xy's, which we found. Let me, sorry, move this out of the way. I can just look in here. The sum of the xy's, 8254, minus the sum of x, which we found was 372, the sum of y, which was 112, over sample size times the sum of the x squares, 24,814, minus the sum of x, which is 372, squared. Okay, so we'll calculate that. And again, you might round in slightly different places here. Should be close. Oops, I should have put, let me start over. Parenthesis, make sure you put the whole top in a parenthesis. 82, and the whole bottom, minus. And again, the best thing to do is try to type this in your calculator all in one step. Just make sure you put the top in a parenthesis, the bottom in a parenthesis. You don't want to kind of calculate some of it round, calculate some of it round, and so on. You don't want to do that. So I'm just gonna, I got 74857, so I'm just gonna round this up to 0.75. I'm just gonna tell you we're gonna draw this on the graph, and so you don't want to, you want to think about how precise you can actually be using things on the graph when you're thinking about rounding. All right, so let's figure out B. B said take the average Y value minus your B value you just found, 0.75, times your average X value. And so I'm going to do that. 18.67 minus 0.75 times 62. And I don't know, I'm going to say that it's 27.83, but I'm going to say -28. We'll say -28. Okay, so my formula, y hat, is the A value plus the B value, X. So there is my estimator for the response variable. All right, so that's C. That's what it asks us to do for C. For D, graph your least squares approximation, least squares line on your scatter diagram, be sure to use the point average x, average y as one of the points on this line. So I'm gonna go back to this picture. It says use this point, average x, average y on there. So I'm gonna make sure that I put that on there first. So 62, I think that's right on where the axis used to be, right in the middle here. And then 18 point, it's about 19. Just I'm gonna put that dot right there. And then my line, notice the B, the marginal rate of change, or marginal change, is 0.75. Well, that's 3/4. That's up 3 over 4 if you think slope, up 3 over 4. So from this dot that I just put, I'm going to go 1, 2, 3, 1, 2, 3, 4. And I'll put another dot there. And I can count down 1, 2, 3, and back 1, 2, 3, 4. I'll put another dot there. And what I would like is to have a ruler here, but this pad, it doesn't tell me anything. So I don't know how straight I can make this, but let's see if I can kind of track where this is at. So there, there. I think that might be okay. So I'm going to try that. Okay, is that you can do better on your paper than I can do here. It should have went through those, but you can kind of see how this data point's a little bit above it. This little data point's a little bit below, a little bit below, a little bit above, a little bit above, a little bit above. That's where I was supposed to go through. This one's a little bit. So they're kind of, it's kind of zooming in between those the actual data. I guess this is not a data point. This was supposed to be. I was supposed to hit that. So it's supposed to go like that. So it's pretty good. It's pretty good. Some of these are almost right on top of it, whereas the other ones are a little bit off of there. But it's not bad. And if I was drawing this on a piece of paper, I'd probably do a lot better job than I'm doing on this tablet here. But you kind of get an idea what that should look like. All right. So like I said, hold off on E and the R value from B. We'll get to that in a second. But if we want to use our linear model to predict a value that falls between X values within the data set itself, this is called interpolation. So you think about if I wanted to try to predict, what would 52, what would it be for 52? Or 61, a 61-year-old, what would that be? I could make those predictions now using this date, either this line, if I did a better line, using the line, or the equation, which would probably be a better option to calculate that. I can make some predictions about those values, and they would be pretty good based on that data. And that's called interpolation, when you're picking a number between those data values. Now, if you try to expand outwards beyond the data set you have and say, okay, well, let's use it to predict what, this data set begins with 37-year-olds. Let's try to, would it tell us about 27-year-olds? Would it tell us about, 31-year-olds? Would it talk, what if we expand it the other way? Would it tell us about someone driving when they're 100? How would this predict values for those outside the data set? And the answer is that's called extrapolation. And it could, but it might not actually be valid. It might not actually make sense for that. For example, if I just look at the graph and I say, okay, well, what if I wanted to backtrack it to 17-year-olds? Well, this would end up in the negatives. It's like, what would that mean? How could you have a negative value for the percent of people who die in car accidents, that it being because of, that doesn't even make sense. So outside of this specific data set, I might not be able to make any predictions, or it may not even follow the same pattern You know, remember we talked about how you could look at a data set and you could say, well, that looks like it's a linear positive data set. What about this one? This one looks like maybe it's a negative linear data set. But then there was also things that were not linear. So you might have something that looks like this. You know, this could be the real situation. And, you know, like young people, it has a lot of accidents because they don't yield the right away because they're unexperienced. But then like you hit a point where like a lot of people driven enough that they've gotten experience, and so they don't have those kind of accidents very much anymore. And then it starts increasing again, you know, as people get older, maybe their sight starts to go, they have a hard time seeing other cars so that they can yield correctly or be aware of it. And so we might just be looking at like this area, you know, and saying, hey, that looks pretty linear, but the entire data set may be more parabolic, you know? So once you start getting outside beyond the actual values within the data set, this prediction becomes a little bit more questionable. You're not exactly sure. Within the data set, you can feel pretty confident that it's a good estimator. But outside of that data set, maybe, maybe not. Now, that doesn't mean you would never use it. Yeah, you would. You would use it. It would be a starting place to say, hey, we think it's going to go here. But that doesn't mean it necessarily will. You just have to say, I can't be very confident about this, but I'm going to make a prediction about it. So you still make those predictions. You just aren't real confident about it. All right, so let's look at 12F. F says, predict the percentage of all fatal accidents due to failing to yield the right of way for a 70-year-old. So we have our equation, right? We have our equation here for our estimation for this. And it's a negative 28 plus 0.75x. So let's make this, let's see how or what we would get if the person was 70 years old, you know, using our thing. So we're just going to calculate that. Negative 28 plus 0.075 times 70. Oops. That doesn't seem right. Oh, I put my decimal in the wrong place. Let's try that again. 0.75 times 70. Okay, so it looks like for 70-year-olds, the percent of fatal car accidents that could be explained by failing to yield the right of way would be 24.5%. Okay. And you know, again, it might not be exactly that. It might be 25, might be 20, you know, 3.7, but it's going to be around that area. It's going to be close to that. And that's because this is an interpolation, right? 70 falls between the minimum of 37 and the maximum of 87 values we got. So within the data set, that's a pretty good prediction, we could say. Again, it's not perfect, not 100% match, but it's going to be probably pretty close. All right, coefficient of determination R squared. So what this does, first in section 9.1, we calculated R, the correlation coefficient. We figured out how closely the data set, how strongly the data set fit a linear relationship. In fact, how closely it fit a linear relationship. And obviously, the closer it gets to 1 or -1, the stronger that is. The closer it gets to 0, the weaker that relationship is. What we're going to do is we're going to take that value and we're going to square it. Right? We're just going to square it. It's always a value between 0, -1, and 1. So it's always going to come out positive when you square it. This is going to tell us what percent of the variation from what we expect to get to what we actually observe getting is kind of explained from this least squares method. So we're going to do that. We're going to use that least squares method, get our line. We're going to be able to predict a value from that, and the observed value is going to be slightly off. And that explanation of why that, how much of that offness we can measure using this R squared value. Now, the amount that we're off by that we can't explain some way, that's the complement. 1 minus R squared is going to tell us what percent is not explained, some way. So this is going to give us some kind of measurement of like how predictive, again, it's kind of like R predicts how much it looks like a line. R squared is going to say how well that line fits the actual data, as a predictive value for it. Obviously, the bigger R squared is, the better we can say it predicts values versus 1 minus R squared. It's going to be, less predictive for it. Okay, so let's look at 12E. 12E says, find the value of the coefficient of determination. What percentage of the variation in Y can be explained by the corresponding variation in X and the least squares? What percent could be unexplained? All right, so we need to find R. So we're going to need all those things to find R. And again, they gave us an R value. They said it was negative 0.943. I'm just going to go ahead and calculate it, see if we're right. That sounds right. So again, I'm going to calculate R. Just a reminder, you take your sample size times the sum of your XY. So I'm going to go to my table here. Sum of my XYs is 8254 minus the sum of X, which was 372 times the sum of Y, which was 112. All of that over the square root times another square root. Right. Within the square root, it was sample size times the square of the x's, 24,814 minus the sum of the x's being squared. And then the same thing, 6 times the sum of the squares of y minus the sum of the y's being squared. Okay, throw that in our calculator, see what we get. And again, when I put it in the calculator, I'm not going to use all the parentheses, but make sure you put the top in a parenthesis and the bottom in a parenthesis so it'll work out right. 6 times 8254 minus 372 times 112 divide by square root. Get out from the square root times another square root. Get out of the square root, close the bottom. All right, let's see how well I did. Not well. Looks like I messed up some kind of calculation somewhere. That is not R. Oh, I know. Let's try this. Well, that's better, but it's still not right. Oh, okay. Yeah, double check your work. Looks like I'm leaving off some keystrokes here. Ah, here we go. Now I gotta, this says there should be negative. Oh no, that's, sorry. No. I got the right value, but I didn't get a negative. I don't think it should be negative. I think that's a typo because the graph is a positive slope. So yeah, this is, I got 0.943 and the book says it should be negative 0.943. Well, that's wrong. It's not negative. It's you can look at the graph. It's obviously going to be a positive slope. So it's a positive. This is a strong positive linear correlation, right? That's very strong, 0.943, but it's going to be positive. It's not going to be negative. So either that's a typo or they were just trying to make sure we were checking it and we weren't just using the value they gave us. Now that's R. That's not R squared. R squared. So we're going to take that 0.943, square it, and I'm just going to use this value in my calculator and square that. And I got about 0.89. 0.89. Right? So that is the value for the coefficient of determination. So what percentage of the variation y can be explained using the corresponding? So 89% can be explained. Okay. So that's how closely our observed data are following our predicted values. So that's explained, but there's some variance. It's off. So what percent it cannot be explained? 11% can't be explained. So there's some. So we're not following perfectly, and that 11% is how far off we are. All right. That's E. Okay, so that's 9.2. Go ahead and do problems 1 through 4 all, and then 7, 9, and 11. And again, for 7, 9, and 11, the actual directions, though they will oftentimes ask you for like a part F, but the actual directions start at the bottom of page 561. There's an A, B, and then continuing on to the next page, C, D, and E. And then usually there's also an F in the actual question itself. So make sure you do that. You might want to check those values. Like for example, this one had a negative R value when it should be positive. So please check those, verify those values. All right, and that's all we're going to do for this section. We'll see you later.